class we were going to focus on means. So we'll go over the homework that dealt specifically with means, and then we're going to move on to proportions today. On Friday, I hope you all come because we're going to do a fun activity. So please come. Oh, no, it's going to be fun. We're going to throw balls at each other and play with conversation hearts. You look beautiful today. Wow. Oh, you created this. Anyway, so we're looking at questions 36, which was the potato chip bag question. From start to finish, I think we've been asked, especially the last two problems, so we'll look at those. When you read each of these questions, you have to make the decision, are they talking about means or are they talking about proportions? And when you read question 36, they do say that the mean is 10.2. So they give you, actually they give you a normal model. And let's actually go ahead and write it in the correct notation. Do you remember how we did this before where I said N stands for the normal model, and then we write the criteria as the mean and the standard deviation here. So the mean was 10.2, and the standard deviation that was given to us was 0.12. Okay? So that's going to be the normal model that's described from the packaging machine. Okay? That's the individual machine has that distribution. Okay, fair enough. If we keep reading here, it says, what fraction of all the bags sold are underweight? By the way, it states on the bag that they're 10 ounces, correct? And we kind of have a little bit talked about this scenario with the M&M bags. Remember how we did that with normal probabilities and we all weighed the bags and we found out that the weights were actually more than what was stated on the bag? You guys remember that? Okay, so kind of the same type of situation here. So in part A, we're looking at what's underweight. So if the actual mean is 10.2 and the 10 ounces is what's on the bag, then this would be the picture that I would want for you with the shading of what would be considered underweight. Do you agree? Okay. Now, we are not talking about a set number. So we're not talking about the CLT at this time because we're not talking about a sample size of any kind. We're simply just talking about the distribution as a whole. So we're not going to use our CLT at all. We're not going to check conditions. We're not dealing with that. We're just literally, this is just a normal probability question. Okay? So for part A, it's going to simply be normal CDF. And then you have a lower bound somewhere, your upper bound, your mean, and your standard deviation. Okay? So when you do that, the book got 0.0478. Okay, hopefully you got that too. Does that look familiar? Okay, good. Then for part B, question differs, and it says, some of the chips are sold in bargain packs of 3 bags. Okay, right away, I now have a sample size, don't I? Okay, N is equal to 3. So I want to start thinking about that as when I have a sample size, I want to start thinking about the CLT. And I'm thinking about a new standard deviation. Okay? Can I use that formula? Remember, the formula for the standard deviation of the means is the standard deviation divided by the square root of the sample size. But the sample size should be greater than 30, which it's not, but does that matter here? Why does it not matter? Because it's already normal to begin with. So I don't care, right? I don't care about my sample size. Good. Let's keep going. It says, what's the probability that none of the 3 bags is underweight? Okay. So what we want to do here, wait a minute. I'm looking at the wrong question. Okay, sorry. Well, this is actually not even a normal question. It's just talking about probabilities of the 3 bags. So we're not even getting to the CLT quite yet. When it says none of the 3 bags, it means the first one's not, the second one's not, and the third one's not underweight, right? So what is the probability of not being underweight? The reciprocal of this, correct? Which is 0.9522. Yeah. So 0.9522 to the 3rd power. Is that okay if I just do it that way? Because there's 3 of them. Okay? So 0.9, I'll write it prettier. 0.9522 to the third power. Okay, and they got 0.863. Double check my math, or double check their math. Does that look right, Sammy? It's the reciprocal of this. Because that A is the probability that they are underweight. We want the probability that none of them are underweight. So we had to do reciprocal. Okay? Any questions so far? So C and D is where we have the questions come up, right? Okay. So in part C, it says, what's the probability that the mean weight? So now we're thinking CLT, because now we're talking about the average weight. Okay? So what is the probability that the mean weight of the 3 bags is below the stated amount? So we still have 10.2, we still have 10. We are looking at the same situation in part A, except what's now different? The standard deviation is different, right? Because I'm talking about the mean weights. So that means that in this question, I need to find the new standard deviation. So what was it to begin with? 0.12. So 0.12 divided by the square root of 3, the new standard deviation was 0.069, a lot smaller. And so when we do our normal CDF here, everything is the same except the standard deviation is now different. And so when I do that, the probability becomes 0.0019. Does it make sense that the probability is a lot smaller? Because we're talking about the average of the 3 bags is underweight. Doesn't it make sense just to think about contextually for a minute? I could likely, not likely, but it's possible for me to get 1 underweight bag, but the average of the 3 bags to be underweight, we don't expect that to be very likely at all, right? So that kind of makes sense. You want to make sure that your answer makes sense to you, and it should here. Again, the key word in the problem was the probability of the mean weights, okay? That told us right away that we had to find a new standard deviation and use the CLT, okay? Well, hello there, Caps fan. She's here. I will deliver. Okay, part D. So part D says, what's the probability that the mean weight, okay, so now we're, again, mean weight, still CLT, but what's now changed is part D says we have a 24 bag of cases of potatoes. 20, like, you know how you get the Costco bag of chips, and then you have your little 3-pack? So now we have our sample size is now no longer 3, but it's 24. So in part D, the only thing that's going to change is now we have a new sample size, which means that the standard deviation of the mean weights is going to be 0.12 divided by the square root of 24.
So you always start with the original standard deviation?
Yes, always with the original standard deviation. Absolutely. And so they got 0.024 as your new standard deviation. So the only thing that's going to change in the problem is that last number. Okay? The answer here was 0, which means that it's extremely unlikely. It's really not exactly 0. I mean, it's some really, really small number. It's just the calculator won't do it that small. Yeah, it's just ridiculously tiny. So what I would do is use your wavy equal sign and say it's approximately 0, which means that it's, and you never want to say it's never going to happen, okay? Because that means that there's no chance. It's kind of like me winning the Powerball tonight. There's probably no chance, but someone's got to win, right? That grain of sand out on the big beach, it might be Miss Knackert. You never know. Does that answer your questions on this question, though? Anything else? Yes. Just 25C, okay? Let's look at that one. I think the hard part sometimes with these types of questions is knowing when am I using, like in part B, just my straight probability rules. When am I using just the normal distribution? And when can I apply the central limit theorem, where it's normal distribution, but I'm actually finding a new standard deviation? So part C and D in this question, we had the mean weights. That was the clue to us that we're talking about the central limit theorem. And then A and B just really had nothing to do with it at all. All right, so 25C. Okay. So question 25 is about pregnancy, and it says that the normal model, so I'm just going to write out in the correct notation, normal model, a mean of 266 days and a standard deviation of 16 days. I guess that's the gestational period, right? And C says, suppose a certain obstetrician is currently providing prenatal care to 60 pregnant women. What's 60? Sample size. Good. So I'm going to say that my sample size is going to be 60. And it says, let Y bar represent the mean length of their pregnancies. Okay. And then it says, according to the central limit theorem, what's the distribution of the sample mean Y? So basically, we have to double check, in order to use the central limit theorem, we have to check our conditions. So what are the conditions? The first one would be random. Is the sample collected randomly? Nope. Because it's one doctor and his 60 patients, correct? That's not a random sample. So in this case, we would say the sample was not collected randomly, therefore we're going to proceed with caution. And that does happen occasionally, and we just have to prove to the AP grader that you did remember that you needed to check the conditions, even though it may not have checked out, okay? So you're going to say, sample not collected randomly, proceed with caution. Does not have to be in paragraph form. To give myself some room. I just literally do 1, 2, 3 to remind myself that I'm checking all 3 conditions. Okay. The second condition is what? Well, independence, which we rarely can ever figure out. So the 10% condition. So what would we say here? That 60 is less than 10% of what? Yeah, over the course of his whole lifetime, career, whatever, okay? So of all doctors' patients. Did I spell that right? Yeah, you ever look at something and you're like, it doesn't look right?
I think it's like the dot over the end.
Is that what's throwing me off? All right. I'll trust you on that. Anyway, all right. Our third condition is? Sample size is big enough, and there's 2 cases. One is I don't care if it's big enough because the distribution is normal to begin with. Are we in that case? Does it say it's normal to begin with? It does. It's a normal distribution, doesn't it? So I don't really care. But the sample size also happens to be bigger than 30, doesn't it? So it actually satisfies both. Doesn't really need to, but it does. So we can use. So what should we say as our third condition here? So we can say that the sample size is greater than or equal to 30. Actually, we should use the number 60 is greater than or equal to 30. And if you can say that the population is normal to begin with, right? And the population is already normally distributed. You really wouldn't have to do this part and would be still fully correct, okay? Yes, absolutely. Okay? All right, so my conditions check out. Exactly.
For the condition, when it satisfies both, is there like any condition that you have to put down if you call it both, or optional? Like which one's preferred? That both?
It doesn't really Doesn't really matter, I guess. I understand your question. It doesn't really, one or the other. Okay. Okay, so what do I have to do from this point? I have to just describe the model because it's checked out, so I would want to see the conditions being checked. And then you would say the model for the patients, right, is going to be 266 because the mean stays the same, but the standard deviation is now going to be 16 divided by the square root of 60. Do you agree with that? And that's all you'd have to say. You could leave it just like that, and you would get 100% correct.
With the 1, 2, and 3 on the
What, baby?
With the 1,
Yes, everything in blue. Everything in blue would get 100% answer. Yes.
So shape would be.
Oh, the shape is normally distributed automatically takes care of shape, center, and spread. The standard deviation. So shape, center, spread. Yep. So if we're asked to describe a distribution, and he's exactly right with going with shape, center, spread. Does it say that in the question, by the way? Okay. So shape, center, spread, and whenever it asks, is always the things that you want to describe, and this notation alone will give you all of that, which is kind of nice.
21 said shape, center, spread, so I kind of like assumed for those three things.
If it says describe a distribution, shape, center, and spread is exactly what you should do. And honestly, I mean, you obviously have to check the conditions, but that does shape, center, spread right there. No. You could write it in words and say normally distributed, the mean is blah, 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 and the standard deviation is blah, blah, blah. Shape, center, spread. Fine. But just that notation is the standard notation for that. Devin.
For like the number 1.
Uh-huh.
Condition.
Bothers you. Could you randomly select from that 60?
Yeah.
No.
Well, no, like, because those aren't random, so it's like you could just pick a bunch of people that were like early by a month.
Exactly. Right. So if you, well, first of all, you have to you're given the data. You can't like randomly pick from a data that's already been given to you. You want to randomize from the beginning. Like you randomize the doctor, randomize, put everybody in a hat and whatever you want to do. But when you're taking, like, it's called a cluster sample, if you remember, where you have everybody from one group. So this is actually a cluster sample. It's definitely not random. And we're hoping that it's representative, but I have no idea. Maybe maybe this doctor deals with only high-risk patients that always deliver early. It doesn't say that, but that could be a condition, right? Because there are obstetricians that deal with only high-risk pregnancies. So you have to be really careful about how that data was collected, which is why proceed with caution is such an important sentence here. Good thoughts, though. Good conversations. Excellent. Helpful, better on the homework? Steph? Yeah, one more. Let's go. 26D. Sure. I'd be glad to. All right. So 26 talks about rainfall, and in Ithaca, New York. I think Ithaca, New York's probably getting more than rainfall this winter, right? It's like snowing. Have you all seen pictures from Boston where the snowbanks are just so high? It's just unbelievable. Can you imagine the floods that are going to happen in the spring when all that snow melts? It's going to be dangerous.
I saw this photo. I don't know when it was taken.
All right, so let's write some information down that we know here. So in 26, it says the average is, well, that's not a sample average, is it? It's a population average. So we have an average of 35.4 inches of rain and a standard deviation of 4.2. All right? What, baby? Okay. So in part D, it says, what's the probability that those 4 years, okay? So we have 4 years, which means what is 4? Because this is per year. So n equals 4 would be our sample size, right? So 4 years. So that means that we have to find a new standard deviation, 4.2 divided by the square root of 4. And what do we get with that? Someone tell me. 2.1. I'm just looking at what they did. Yep, 2.1. Okay. And then it says, for D, it says, what's the probability that they get less than 30 inches of rain? So what we're looking for here is putting our mean here of 35.4. We're looking for less than 30. First of all, can I use the central limit theorem? Can I even do this? What would I have to do to check? The conditions. So let's check them verbally. Okay. 1, random. Are those 4 years? Does it say that there was a random 4 years?
No. So you have to
It just says we have to proceed with caution, so we want to say that. Probably number 2, 10%. Is 4 less than 10% of all the years? Yeah, okay. And then the third one would be sample size. Or, well, is the original population normally distributed?
Yes,
It says assume the normal model applies. So because the sample wasn't collected randomly, we're not sure, but we'll go ahead and proceed. Okay? So we have normal CDF. We have negative E99, 30, and then the mean, and our new standard deviation, and we go from there. Is that okay, sir? You good? Remember that this is going to be the mean, and this is your standard deviation. Okay. If you look at the textbook, I don't know if the textbook explanation in the back of yours, they always work with z-scores. I tend to just bypass the z-score formula and go straight and just plug it into here, but it's up to you. You ready to talk about proportions? I am. Yay. Okay. So I'll check homework in a few minutes. Okay? But let's talk about the newer stuff, or the second half of chapter 18, because the first half just dealt with the means, and you were given some formulas that dealt with your mean and standard deviation. The mean of the means is still the mean. That sounds weird. The average of the means is the original mean. And then the standard deviation was just the standard deviation divided by the square root of the sample size. When we deal with proportions, things change a little bit. Okay? So let's go ahead and look at this example. Okay? So I just kind of randomly took a sample. It's a random sample. My sample size is 100. Okay? Which is great and all, but I don't know that the same conditions are going to apply for a for a proportion as it does for a mean. And in fact, they are different. Okay? So there are different conditions that we have to check when we're dealing with proportions. We are interested in the proportion of seniors that have a GPA greater than a 2.0. Okay? NCAA minimum to play a sports at a college, 2.0. So what proportion? So what would I do? I mean, we could go and count, right? We have a random sample, and we could find the proportion. How would I take that sample, and I would have to find a mean and a standard deviation, and I don't want to apply it to the whole county, right? So there's some things that we have to do with that. I mean, we could, if you wanted to, you can kind of go through and cut. So above a 2.0, you could go through and count them, right? But this would only apply for the sample itself, wouldn't it? I mean, you get the idea of what I'm trying to do, right? All right. Let's say that I conducted 10 random samples of sample size 100 and found the proportions to be this, of 2.0 or higher. So in my first random sample, I got a proportion. By the way, p hat means sample proportion. Okay? When you have a little hat kind of like this, means sample mean. The p with the hat on the top of it means sample proportion. Question? Yes, yes, yes. So that's exactly what that means in this particular case. So each of these samples was 100. So, and Devin's right. In my first sample that I collected, 78 of those out of 100 had a 2.0 or higher. Do I expect there to be some variation from sample to sample? Sure, I expect there to be some variation because I know that when I collect a random sample, they're not going to be exactly alike. But they're kind of close, right? So we would like to be able to take our random samples and draw some conclusions about the entire population of Prince William County students. Okay? So that's kind of what we're getting ready to do here. Okay? Now, let's move on. All right. So as we draw more and more samples, okay, the sampling distribution will become more and more normal and centered at the actual population proportion. Just like with means, it did that too. It was centered around the actual average. So the mean of the sample proportions is simply the population proportion, okay, which is kind of nice. You with me? Okay. So that's one. So it's centered the true population proportion, just like with means. Awesome. However, our standard deviation has a new formula. So this formula you need to write down. Okay. Now I am not sure how it's written on your formula sheet. So does anyone have one handy? Sure. Thank you. It is written, if you look in the top right, it's not written like this at all. Don't you love that? It's written like this. Okay, do you see that on your formula sheet in the top right corner? You'll see the sample mean standard deviation, and then what I've written in blue is the sample proportion standard deviation. Do you see that there? Isn't Q just 1 minus P? Aren't they the same thing? So it's just your sample proportion, your population proportion times the complement of that divided by sample size. And this is the square root of all of it. So that formula is on your formula sheet, so it is not anything you need to memorize. We just need to know when to use it. Okay? So just like with means, with proportions, we have conditions to check to figure out when we would use or when this would apply. Okay? Sure. The mean is the actual proportion. Remember, P is the parameter. P hat is the sample. Okay? Or is the statistic based on the sample. Okay? Are we okay? Just these two formulas here. Because when we're hoping that we'll be able to use the normal distribution, and anytime we have a normal distribution, we need to have a mean and we need to have a standard deviation. Do you agree? I mean, we need those two things to be able to apply the normal model. So those are our formulas to do that. Oh, and that's what I have here. Great. All right. Here are the conditions that we need. Okay, remember how I said we wanted to kind of branch in our mind? We ask ourselves, is the question talking about means and averages, or is the question talking about proportions? What gets confusing is that it's the average of the proportions. So the word average still might be in there. Okay, so we have to kind of be careful a little bit. But when we're talking about proportions, we're talking about what percent of students have a 2.0 or higher. So you are going to be looking for a percent or maybe a fraction, 20 out of 60 or something like that. So it will be an actual proportion will be in there. The first two are actually the same. Okay, the first two conditions are the same. So once I've decided I'm in the proportions branch in my brain, I'm going to check those conditions. The conditions, the first two are the same for both. It's the third one that's different. With the means, we had to see whether the distribution was normally distributed to begin with or the sample size had to be greater than or equal to 30. When we're talking about proportions, you have to check this. Now again, Q is just 1 minus P. So N times 1 minus P hat is greater than 10. Okay, either way. Your book calls this the success-failure condition. Okay, so you might see that written that way. And you're just double checking, is the sample size times the proportion greater than 10, and so forth. Okay? And it actually should be P and not P hat. But we'll leave it for now. The reason that I put that in there is sometimes we just don't know what the population proportion is. Kind of like the standard error like we talked about last time. Okay. You ready to look at when we would use one as an example? Come on, you are. You are. There's the only ones. There's 3. 1, 2, 3. And 3 is the only one that's different. Okay? All right, so let's look at an example. Still sticking with this GPA idea. Okay? Suppose that the true population proportion of students in Prince William County with GPAs above 2.0 is 71%. That percent sign is a dead giveaway that you're dealing with proportions. So I already know what branch in my brain I'm going to. Okay? Is it means, is it proportions? We're in proportions mode. So I'm going to write what 71% is. P, the true population proportion, not P hat. Remember, P hat is a sample proportion, but P is 71%. I'm going to go ahead and just change it to 0.71. Okay? If we take one random sample of 100 students, or is N 1 or is N 100? Okay? What is the probability that we will get a proportion less than 65? Well, we're not trying to find the average of the proportion. So really, what do you think we would do here? So what is the probability that we'll get a proportion less than 65%? Well, we have a 0.71. Would you agree? We want less than 65%. Okay. We have to think about this. We're just doing one sample of 100, right? We're not finding the average of all of my samples. A little bit different, yes. That's where I'm going with this. Is it 1, is it 100? That's what we're trying to describe here, okay? So we actually, let's make sure can I just check something real quick? Yeah, okay, good. Okay. Am I going to use the CLT as my question with proportions? What would I do here? Okay, so let's look. Is it 1, is it 100 is my question. We have one sample and it's 100 students. And so that's where our question becomes here. So let's just go through and see what would happen if we did 1 versus what we did 100. And let's see if we can clarify in our minds which one it should be. So what is it random, first of all? Let's go through our conditions. Is a sample collected randomly? Yes, okay. It even says it in the problem. How about 10%? Well, we've got to figure out what n is, right? Either one, would you agree? 100 is less than 10%? Okay. So, and 1 is definitely. So we're going to say 100 is less than 10% of all the students in Prince William County, because that's our sample size in this particular sample, right? Okay. And then 3, what's the condition that I'm checking? What's the new one? Okay. So it should be NP is greater than 10 and NQ is greater than 10. Okay? And that's why I said it shouldn't be P hat. It really should be P and Q. Sometimes we have to estimate with P hat, but that's a long story. So anyway, so N is going to be 100, right? P is 71. Is that greater than 10? Yeah, okay. If I did 1, that doesn't really make sense, does it? Okay, so we really are having a sample size of 100 because that's the number of students we're doing, not the number of samples that we're collecting. A little bit different. How about over here, what's Q? It's the complement of 71, so it's going to be 0.29. Is that greater than 10? Sure. So you actually need to show me those calculations. Are you with me? It's required. Show me the numbers. Okay? So we actually need to change this. Okay? So what do I do? I need to find something, don't I? Do I need to find my new standard deviation? Okay? And so what would that be? Notice my notation, because I'm dealing with proportions this time. It's the standard deviation of the sample proportions. So it's going to be, what was the standard deviation? Did it say? Did it even say? Oh, no. Oh, that's because we have the new. It's, what is it? The square root of 0.71 times 0.29 divided by, there you go. Okay? Another clue that we're dealing with proportions is that you will not be given a standard deviation in the problem. Weren't the means questions you were given a standard deviation every time? So here we're not. So that's another clue that we're dealing with the right thing. So I don't know what this is. Does anyone? 0.045? 0.465? 0.45? Are we all trusting Hunter? Yeah? Okay. He's trustworthy. Okay. So how does that help us? Why do I need that? Yep, to be able to apply the normal curve, right? So now we're going to look at our picture and we're going to say the probability is normal CDF, lower bound, upper bound. What's the mean? Yep, 0.71, and then the standard deviation is 0.045. What'd we get? What'd you get, Sammy? Do it for me. See what we get. I'm hearing all kinds of different numbers. 0.091211. 0.092? Is it 0.091? All right. Okay. So let's think about this. Does that probability make sense that it's small? Well, if you look at the picture, it should be less than 50, right? And you know, if we're trying to figure out, just in context here, if we take a sample of 100, how likely is it that our proportion will be less than that much less than the average? Not very likely. Okay, good. What changes in this question? Which affects what? The standard deviation. Okay. So if we take an even bigger sample, what do you expect is going to happen to our probability? It'll get even smaller. Good. Even smaller. And that happens here. All right, last question that I'm going to do with you, and then you're going to partner up, and I'm going to pair you up. Yes? Oh, I just said that if we take a sample of 250, an even bigger sample, how likely is it that our sample proportion will be even less? It'd be smaller. That's exactly right. Exactly. Yep. It decreases as well. It decreases.
Yeah, so there'll be more standard deviation.
Yes, it will take you more to get further away. Yes. Yes. I'm sorry. Yes, that's true. You right back there, Monica? You sure? It's hump day, right? Okay. All right, last problem we're going to talk about. Good old hepatitis. Statistics is always about death and dying. It makes me so sad, okay? But it is. Not that hepatitis is death and dying, but it's a disease, I guess. So cardiac patients who contract hepatitis is 0.07. What is 0.07? Is that P? Is that P hat? Is that N? Is that Q? What is it? It's your population parameter, isn't it? That's what we think. So The claim, you'll hear me talk about this a lot, the claim is that P is 0.07. Okay, now, be very careful because there are lots of P's. There's something called a p-value, which is something that we introduced last class, but you don't know what that is yet. So if you, please know that that means a capital P, okay? Notations kind of gets a little hairy here over the next couple of weeks. All right, a new blood screening procedure is believed to reduce the incident rate of hepatitis. Don't you love my spelling here? Okay. Blood screened using this new procedure is given to 200 patients. What's 200? Sample size, good. Notice I'm pulling out the information from the problem and writing it down. I want you to do that. I want you to identify each of the variables. Only 6 out of 200 patients contract hepatitis. What's that? Well, p-hat. It's my sample proportion. In my sample of 200, 6 contracted hepatitis. So that's my sample proportion. What is 6 out of 200 out of way? Anyway, isn't it exactly? Oh, okay. All right, so we think it's a favorable result because it appears as though this new procedure reduces the rate of hepatitis. But is it enough information? Okay, do you think that it's enough to say yes? It's enough, or could it just be by chance? It's just because samples vary from sample to sample, don't they? So maybe this sample just happened to be low. So this is kind of like the question we asked before. How likely is it that we could get this as a result of chance? Okay? So what do you think we should do? How would we answer this question? Let's check our conditions. Let's do that first. We want to be able to apply the normal model, but what are the conditions to do so? Okay, is anyone smelling onions, or is it just me? It's making me hungry. It's like some kind of cooking class. I don't know. Come on, Sammy. Your neck hurts. Oh, I'm sorry. Onions don't help? Okay. Is it collected randomly, by the way? It doesn't say, so what are we going to have to do? Okay, so we actually need to say that. Random sample. We can say random sample is assumed. I hate the word assume. You know what that does? It makes a out of me and you, or you and me, but okay. What's the second condition? So, well, don't just say yes. Use numbers. 200 is less than what? Of all cardiac. Thank you for saying that. All cardiac patients who contract hepatitis. Nice. Well, let's think about that. Is the population that we're worried about all patients, or is it all those who contract the disease? All those who contract the disease, because we want that population to get smaller, right? So that little part that Hunter added is pretty clear. Cardiac patients who contract hepatitis. Thank you. Okay, so we have to check this last condition. This is our new one that we have for proportions. And so our sample size is 200. So we're going to say, is 7% of 200 greater than 10? What is that number, by the way? Thank you. Barely, but it is, right? So that actually, this condition, if you're ever going to do a study, which you all are at the end of the year, and you're going to do something where you ask questions and you calculate a proportion, this last condition tells you the minimum sample size you have to have, doesn't it? Okay? So we have 200 times 0.93 is greater than 10. And what do we get? What's 93% of 2? Oh, thank you. You scared me to death. That's okay.
I just realized I forgot to give that to you.
Yeah, I don't want it. That's okay. 93% of 200 is? Thank you. Definitely greater than 10. All right, so I've checked our conditions. Now what? We're going for a long time. All right, so let's draw a normal model because we think it applies. What goes in the middle here? Thank you, baby. What? What goes in the middle? 0.07, the true population proportion. We're looking for 0.03. What's the likelihood that it could be this or less? What's that probability? Okay? What's the tail probability here? So, we have to find our new standard deviation of our proportions. So it's the square root of 0.07 times 0.93 divided by 200. I'm going to trust you. Hunter's been pretty trustworthy so far. So not very, so 0.018. Is that small? What's small enough? So Devin suggests more than 3 standard deviations away from the mean. Okay. Which is this, by the way? It is. I guess that's not really my question, though. Like, my question is how low do I want this probability to be? Well, so that's a question we're going to answer next week, okay? Because there is an answer to that question, okay? It depends on the strength of your test that you want to do, and so we'll come across an answer to that very question. But let's go back to answer this one. Is this sample enough to convince us that the real long-run proportion has been reduced? So is this small enough to say, yeah, I think that this test is good to go? Yeah, well, probably, okay? Again, we'll revisit this and figure out, is that number small enough? This is actually what's called a p-value, okay? And the p-value has to be less than, has to be real, real small. The smaller the p-value, the more likely that it's a good thing, okay? That the test would be successful. Good. All right, so what I want us to do here is I'm going to pair you up with someone. So listen for your names. I'm going to randomly do it. So Stephanie, you're paired with Nathan, okay? Deja, you're paired with Tanner. Amanda, you're paired with Devin. Sammy, you're paired with Lena. Charles, you're paired with Daniel. Jordan, you're paired with Isaiah. Kyle, you're paired with Monica. Erica, you're paired with Brian. Judith, you're paired with Evie. Jasmine, you're paired with Hunter. Maddie, you're paired with Zachary. And Sean and Lindsay. Is everybody here today, actually? Sweet. All right, go ahead and move with your partner, if you would, please. Sit next to them. Once you guys are finished, there's about 15 minutes left in class. Once you're finished, your homework is in the textbook. It's up on the board for Friday, okay?